Session again, everybody. So just now we have done with electrical energy and power. So now we would like to do cell EMF internal resistance. So before I start, let's define what is cell, what is internal, what is EMF, and what is internal resistance. Look at here. First, I would like to explain you the brief, outline of a cell. Normally, you are going to study a very detail about cell in chemistry. All right. No, the cell which I am going to talk about is electrolytic cell. All right. So normally, electrolytic cell consists of three important components. One is this is called electrode. This is what we call as electrode. We have two electrodes. One is called cathode, another one is called anode. Anode is a positive electrode. This is a positive electrode. Positive electrode. And this is a negative electrode, which we call as a cathode. This one is the anode. And then we have what we call as the electrolyte. This is the solutions. All right, this is what we call as electrolyte, or we call as electrolytic solutions. All right, we have two electrodes and electrolytic solutions. All right, so this normally consists of for simple cell we use hydrochloric sodium H2SO4, all right, sulfuric acid. All right, so this is what we will be talk about, and two electrodes, one is positively in charge, another one is negatively in charge. All right, so this is what we talk about a cell. All right, cell consists of two electrodes and solution which we call as electrolyte or electrolytic solutions. What normally happens is the solution is undergoing a chemical reaction which we call as electrolysis, because of which this become positively charged and that become negatively charged. Look at here. Just to give you a brief explanations. I just take an electrolyte and I'm going to dig two electrodes. Normally, if positive is copper and negative is zinc. As soon as I dig these two electrodes, the chemical reaction is taking place, and this is what we call as electrolysis taking place, due to which there is accumulation of positive charge and there is accumulation of positive negative charge and accumulation of positive charge taking place until it attains equilibrium. Why it attains equilibrium? Look at here. I just cut this supply. All right. When I cut this supply, what happened is, all right, it attains equilibrium. When it attains equilibrium, there is no current. Right? Current in a cell is going to be zero. And I say this is the potential at positive side, this is the potential at negative side. So potential at negative electrode is negative, potential at positive is positive potential. And look at here, this is a positive potential with respect to solutions, or I say electrolyte, and this is a negative potential with respect to electrolyte. So since there is no current, right? So therefore potential throughout the electrolyte, right, remains same. Potential throughout electrolyte remain same or constant. So there won't be any flow of a charge, movement of charge taking place inside electrode. Why? Because the potential remains same throughout the electrolyte, right? So therefore, what is the potential difference? This is what I call as N. This is what I call as P. The potential difference between I say a potential difference between P and N is given by V plus minus V minus, and I say this is what we call as plus V minus, which I call as, and this is what we call as EMF. And this is when I is 0 in electrolytic solutions. So what is EMF? Now EMF is what we call as, this is EMF. This is EMF. This is EMF. This is what we call it. Now what is the role of cell? What is the role of cell? What is the role of cell? And I just told you last class that we need to supply a power to a wire so that there is a steady flow of charge. So the role of cell is to maintain steady current. And the role of cell is to maintain a steady current. And how cell could maintain a steady current is that cell is to maintain a potential difference. Maintain potential difference across a wire. This is what we have. So what is the role of cell is to maintain a steady current. And how to maintain a steady current is cell maintains a potential difference. The potential difference across a wire. The potential difference across a wire would remain same so that there is a steady flow of current. Alright, so this is very, very important, right? So now look at it. How cell would maintain a potential difference? Cell has EMF. What is the EMF? This is going to be EMF, right? So EMF is going to be the potential difference between positive electrode and a negative electrode when there is no current, right? So I just say EMF is this when I is 0, when a current is 0, when circuit is open. So what do you mean by EMF? EMF is the potential difference between a two electrode, positive electrode and a negative electrode when there is no current, when circuit is cut off, alright, when circuit is open. Three conditions, all are same, one and the same, right? So I just say EMF is a potential difference. EMF is nothing but potential difference, alright, when between a two electrode when there is no current. And EMF refers to electromotive force. EMF refers to electromotive force. So when I say electromotive force means it is something like a force. EMF is not a force. EMF is what? Potential difference. EMF is what? Potential difference. I would like to write here EMF. EMF is potential difference. Is potential difference. And why we have used term called EMF? This is just maybe a long time people thought that there should be some force which has to push a charge from one side to another side. So that is why they coined name like the EMF. Alright. However, literally this is wrong. Why? Because EMF is nothing but potential difference. A potential difference when between a two electrode when there is no current. So that you should keep in mind. EMF is Normally, it stands for electromotive force. However, it is not a force, it is potential difference. Potential difference between two electrode when there is no current. So this is very, very important, right? Now look at here. Now if there is some current, if I say there is some currents, if there is some currents, then what is going to be, right? Then if there is some currents, then look at here. Again, this is another. All right, copper electrode, magnesium electrode. This is a just simple diagram. Cell. Now look at here. Now look at here. Now I just write here. Simple, right? Cell. Now this EMF. This is, let's say this is a cell. Now this is connected to some resistor R. Now this is connected to some resistor R, and then what is going to be is there will be a current. There will be a current. This is EMF E. All right. I will figure out this in a bigger way. This is negative electrode. This is positive electrode. All right. This is positive potential. This is negative potential. All right. Now look at here. When it is connected, when a switch is on, if there is a current I, then what I'm going to write here is, voltage across R is going to be V, which is equal to V plus V minus IR. I is the current. All right. So look at here. This is going to be V is going to be EMF minus IR. I is the current in a wire, right? All right. So this is what we have. So there, what is going to be EMF? EMF is going to be V plus IR. What is V? V is voltage across resistor. This is voltage across resistor. This is a voltage across resistor. Alright. So that means the EMF. Now this is small r is what we call as internal resistance. This is what we call as internal resistance. When there is a current, alright, when there is a current, alright, when there is a current goes through our electrodes, and an electrode offers some resistance, and that is what we call as internal resistance. Internal resistance is a resistance offered by electrode is what we call as internal resistance. Alright, so this is what we have, and then what I'm going to do is now, this is going to be IR plus IR and I divided by R plus small r. Finally, I is going to be EMF R plus. This is current. This is going to be a current. This is a current. Alright, this is the current. So this is internal resistance. And this is the resistance, external resistance, that is the resistance through which voltage, current pass through it. And now look at here. So I can remove this to zero. If I use a copper, it is almost zero. So therefore, I just say maximum current. Maximum current which can be drawn from cell is going to be. This is going to be a maximum current one can draw from cell is going to be this. Why? Because you can't avoid internal resistance. Internal resistance is within that cell, within that cell. So therefore you can't remove it. You can remove this by using a copper wire. Copper wire has almost zero resistance. So this is the maximum current. This is the maximum current. So this is how we have, right? So when I is not equal to 0, so for here, when I is not equal to 0, so I connect this, alright? So there will be, so whatever EMF, look at it in a simple word, whatever potential difference, right, between two electrode is some portion is given to this, and some portion is given to this. There I can say internal resistance. Alright. So therefore, this is going to be V plus R. Alright. So this is what I have. So we talk about internal resistance, we talk about cell, and we talk about EMF. So this you should keep in mind. Very, very important, right? Now what I'm going to do is, now I would like to find out the combination of a cell, right? Cell in a series combinations, cell in a parallel combinations. Cell in a series combination and cell in a parallel combinations. So before I write this, whenever we talk about cell, it has some internal resistance. Whenever we talk about cell, it has some internal resistance. So therefore, I would like to write this. Whenever we talk about EMF, this is going to be I. Alright, this is going to be like this. Or V is going to be IR. Alright, so V is going to be EMF minus IR. This is a resistance group. This is what I have. This is very important, right? Now, what we would like to sell in a series combinations, right? So first, I just sell in series combinations. First, I would like to do cell in series combinations. So normally cell we represent like this, and this is internal resistance, this is EMF. This is how we represent a cell, internal resistance and EMF. So look at here, now I am going to have two cells. EMF 1, internal resistance R, EMF 2, internal resistance 2. This is A, B, C, I current I, current I. This is what I have. Alright. I is a current passing through. So I just write here, I is a current passing from passing through cell 1 and cell 2. This is what I have. So now what I would like to do is, I would like to find out potential. So for cell 1's potential difference, potential difference between A and B, I write this is equal to VAB equal to VA minus VB, which is going to be EMF 1 minus IR1. And now next is a potential difference between B and C is going to be B and C. This is the potential difference, right? So the objective here is to find out equivalent EMF. This is what I'm going to write now. So objective here is to find out, I'll write here, to find out equivalent EMF. If I combine the two cells, what is equivalent EMF and equivalent internal resistance. This is what I am going to find out. Okay. So now I just say potential difference. Now I am going to write this potential difference between A and C would be, this is the entire two cell, which is going to be VA minus VC, which I can rewrite this as VA minus VB plus VB minus VC. Nothing, this is same, right? I just write it in a different form. Now, which is equal to, now I say potential difference between V and C is going to be a V, which is equal to, how much is this? This is going to be EMF 1 minus IR1 plus, how much is this? EMF 2 minus IR2. So therefore V is going to be EMF 1 plus EMF 2 minus IR1 plus R2. This is EMF. Look at here. Now this is going to be this is the potential. This is the potential across A and C, that's combined the two cells. This is going to be equivalent EMF minus equivalent internal resistance. Now look at here. What about equivalent internal EMF? Equivalent EMF is going to be, this is how I write. You go on adding up. If I have a 4 cell, E1 plus E2 plus E3 plus E4 goes on like this, then equivalent internal resistance is going to be R1 plus R2. Alright, this is our objective, right? Alright, this is how we got it. Alright, now look at here. Now what I'm going to do here is, if suppose I just do a cell connection in a different way, that means if I make this such that if I do connection like this, if I do connection like this, then you should know that this is going to be a negative. Alright, then EMF is going to be, then equivalent EMF is going to be EMF 1 minus EMF 2, whichever is greater. If I say, if this is greater than this, then the current will go like this. Alright, so this is how we get it. If E2 is greater than E1, then current would go like this. Why? Because equivalent EMF becomes negative now. So current goes from this side. So that you should keep in mind. Alright. So if a positive terminal of negative terminal of cell is connected to negative terminal of another cells, then EMF is going to be minus. Why? Because, so if I say if E1 and E2 is equal, if E1 is equal to E2, then equivalent EMF is going to be 0. There won't be any EMF or potential difference. So this is one. So the conclusion here is that equivalent EMF of a cell is algebraic sum of EMF of a cell. Why I have written algebra? Why I've told algebraic means if a cells are connected in a same pole or same church. If I say if a negative terminal is connected to a negative terminal like this, so then this has to be a minus or subtractions. If this is otherwise, it is going to be a positive, right? And then internal resistance is going to be R1 plus R2. This is cell in series combinations. This is what we call as cell in series combinations. Now I would like to do for cell in a parallel combinations. And now you can walk forward 3 cell also. Alright. And equivalent internal resistance is going to be R1 plus R2 plus R3, and then EMF is going to be EMF 1 plus EMF 2 plus EMF 3. Okay. Now cell in parallel combinations. Cell in Cell in parallel combination. So this is little different from a series combinations. So instead of series, I'm going to write parallel, right? Instead of series, I'm going to write parallel. Right, cell in parallel combinations. Okay, now again our objective is to find out equivalent EMF and equivalent internal resistance. So here what I'm going to write here is, I'll be having a two cell. Look at here, this is cell 1, this is cell 2. Let's say this is going to be a B1, this is going to be a B2. EMF 1, internal resistance 1, I1, EMF 2, internal resistance 2, I2, this is going to be I, this is going to be I. This is what I have. Now, look at here. I1 is the current in first cells, current in first cell, and I2 is a current in second cells, second cell, and the total current, right? So I is the current goes into V1, and I is the current comes out from V2. So now what I'm going to do is, what is potential difference between A and B1 and B2? So potential difference is going to be, I write here potential difference, that is B between B2 and B1 is going to be E1 plus I1 R1. Again, I write potential difference between a B2 and a B1 is going to be 2 plus I1 I2 R2, and both potentials are, let's say, V, same potentials. Why? Because these are parallel connections. These are parallel connections. Alright, I just realized current. Now look at here. Now what is the total current? I say total current is going to be I1 plus I2. I1 plus I2. And how much is I1 and how much is I2? Look at here, I write here, how much is I1? I1 is going to be I1 is going to be I'm sorry, this is going to be a minus, this is negative, this is negative. Okay, this is negative. So I1 is going to be EMF, okay, minus V divided by R1, and I2 is going to be EMF minus EMF 1. I'm sorry, this is EMF 1, this is EMF 2. V remain same, R2. This is how I'm going to get it. Is simple, right? I'll just do the simplifications. So I2, I1, R1 equal to, goes this side, and EMF 1 minus V, and I1 is going to be EMF 1 minus V divided by R1. It's simple, right? Now we got I1 and I2. Now we got I1 and I2. And similarly for I2 also. Now, so look at here. Now for I1 and I2. So I is going to be, what is I1? Divided minus V divided by R1 plus 2 minus V divided by R2. So our objective is what? Is to write it in this form. Right? In this form. Right? Our objective is to figure out equation in this form. V is equal to EMF minus IR. Alright. So to do that, what I'm going to do is R1 minus V by R1 plus E2 by R2 minus V by R2. And then I just do simplifications. I is equal to EMF 1 R1 plus EMF 2 R2 minus V R1 plus R2. So some simplification here. R1 R2 V R1 plus R2 divided by R1 R2. Now I'll bring V this side and I that side. So V is going to be, in exam you don't need to write all these steps. You can jump. Alright. Now V is going to be this. Alright, I'm sorry, here is minus I one R2. This goes up. I R1 R2 divided by R1 plus R2. This is what we got. Alright, now what I do is I just cancel these two. Cancel out. And then finally we'll get V is equal to E1 R2 plus E2 R1 divided by E1 plus R1 plus R2 minus I R1 R2 divided by R1 plus R2. This is what we get. And I said this is going to be equivalent EMF. And this is going to be equivalent internal resistance. Alright. So I can figure out this equation as this is equivalent EMF minus I equivalent EMF equivalent internal resistance, and this equivalent is going to be 1 this is, and then R equivalent is going to be R1 plus R1 into R2 divided by R1 plus R2. This is how we get it. All right. This is how we arrived for cell in parallel combinations. Cell in parallel combinations. Look at here. I can rewrite these equations. This equation that is 1 by R equivalence is equal to 1 by R1 plus. This is why, because this is in parallel combinations. This is resistor in a parallel combinations. This is resistor in a parallel combinations. Alright, this is a resistor in a parallel combinations. This is not there in syllabus. This year it has been removed. Resistor in a parallel combinations, series combination, it is R1 plus R2. Resistor in a parallel combination, it is going to be 1 by R equivalent is equal to 1 by R1 plus 1 by R2. This is done in class 10 also. This is what I have. Now what I am going to do is maximum current. What is the maximum current? Maximum current is EMF, equivalent EMF divided by equivalent internal resistance. Alright? So maximum current which can be drawn from cell is going to be I max is going to be equivalent EMF divided by equivalent internal resistance, and this is going to be R2 plus R1 divided by R1 R2, alright, divided by this R1 plus R2 divided by R1 into R2. These two cancel out. Finally I get 1 divided by 1 plus, so this is R. This is maximum current. So that means I rewrite this equation like this. This is the reciprocal of equivalent EMF. The ratio of equivalent EMF and the internal resistance is the sum of ratio of individuals cell. Go on, right? So this is all about cell in a parallel company. Now I will give you a small assignments. Now I have done for 2 cell. You go and do for 3 cell. Alright. If you go and go for 3 cell, you get EMF 3 and then internal resistance R3. Alright. So with this, I'm going to stop and just do it for us 3 cell. Alright. So next class we'll be doing meter bridge, then Western bridge, then Kirchhoff's laws now. Right. Thank you.